The previous presentation on soil classification helped us recognize the wonderful insight in the development of the unified soil classification in the 30s and 40s. But we also identified a few limitations that often lead to misclassifications. We build on those concepts to introduce the revised soil classification system in this presentation. The revised soil classification is really very easy to implement. It requires very limited information compared to the unified soil classification, and it is truly insightful and useful for engineering purposes. This is the input information. The percentage passing sieve number 4, the percentage passing sieve number 200. For the sand and gravel fractions, the Emax and Emin, and if you do not have it, then the coefficient of uniformity and the particle roundness. And for the fines fraction, it requires only the liquid limit obtained with deionized water. Now, if you have a soil that is strongly controlled by fines, then you really should know how sensitive those fines are to changes in pore fluid chemistry. Then the classification will ask you for two more values, the liquid limit obtained with kerosene or decane, and the liquid limit obtained with brine. With that input information, it generates three charts. One is the boundaries for behavior, whether it is mechanically controlled or hydraulically controlled properties. And then if you are in the upper part, if the soil is in the upper part, that means the fines play a very important role. The other two additional liquid limits will help you plot on this chart where you will identify the sensitivity of the sediment to pore fluid chemistry. So as you can see, there is a small number of readily available input values, the maximum and minimum void ratios or coefficient of uniformity and particle shape, and the liquid limit of fines. And it identifies both the fraction that controls the mechanical properties and the one that controls the hydraulic properties, because as you will see, the thresholds are not the same. Now, something very important to recognize is that these boundaries that you see on the triangular chart are not fixed and will emerge for each soil. And that makes this classification more complex, but much more accurate and meaningful. And that's the reason why we strongly encourage you to use the Excel file that you can download from our site or the mobile applications that will do all these computations automatically for you. So what is important is also to understand what are all the decisions that are riding beneath this system. And it is all about understanding soil behavior, which is what we have tried to do in the previous conversations that we have had so far. So let's explore those in detail. Once again, this is not needed to implement the soil classification and to benefit from its proper understanding and predictions of behavior, but this will help you understand the underlying concepts that are so critical for classification. So the first one is to recognize the mass fraction when behavior changes. As you can see on the left-hand side, you have a clean gravel or sand with fines. Let's say that this is the clean gravel, and now there are few sand grains and more and more and more, and we have to wonder, when does the behavior change from being gravel controlled to being sands controlled? And as you can see, by the time we are in section C, all the pores are filled with the fines, and so clearly the hydraulic conductivity will depend on the fines after this point, but still the skeleton is being controlled by the gravel. Now, as we add more and more fines, eventually the gravel particles start to float in a sand matrix, and therefore, at this point in point E, both hydraulic and mechanical properties are controlled by fine fraction, in this case, the sand. So as you can see, we have thresholds for hydraulic conductivity, which are going to be different than the thresholds for fluid flow. In previous conversations, we derived these equations, which were the mass fractions of gravel with respect to the total mass of the soil, or sand, or the mass fraction of fines with respect to the total soil mass. And if you begin replacing for some of the void ratios here, you will soon convince yourself that these transitions are not at 50% as predicted or as selected in the unified soil classification. And that is very important to recognize that the finer fractions start to control behavior significantly below or before reaching a 50% mass fraction. Now, for these void ratios, now we have to think which void ratios are we going to choose. For example, we could select that the situation where we have the loosest packing with the loosest coarse packing with the densest sand packing for this transition, or conversely, the densest coarse packing with the loosest sand packing for the first threshold. And so Emax and Emin play a critical role in packing density and in defining these mass fractions. Now, what about the void ratio for the fines? We cannot do an Emax and Emin. We will address this in the next few slides. So once again, for Emax and Emin, for the sand and gravel, we recognize the importance of the coefficient of uniformity and particle shape. This is really a major component of understanding fabric in coarse grains. And this comes all the way from the work by Yao in 1973, and large databases that we compiled and we extended with our own experiments in this paper by Chao. But we can anticipate what is Emax and Emin if you just tell me what is the roundness and the coefficient of uniformity. And this is built in the Excel computation sheets. Now, what happens with the void ratio of the fines fraction? Before the soil is carrying the load, it may exist at, before the clay is carrying the load, it may exist at a fairly low effective stress because all the load is carried by the granular skeleton. But once the coarse grains are floating in a clay matrix, now the clay is carrying all the load. And here is a problem because while sands and gravels, their volumetric density or the void ratio doesn't change much with confinement, the void ratio of clays changes quite significantly with confinement. So this is actually real data behind these charts. This is a high plasticity clay, and as we decrease the plasticity and we go into the silts, this becomes flatter. So please notice that there is an indirect relationship between the void ratio at the intercept here, let's say at 1 kPa. The higher the void ratio, the higher the slope of the line, the C sub C coefficient for remolded fine-grained materials. And in fact, this is the case. This is the void ratio at 1 kPa, in other words, these intersections here, versus the compression index for a large number of soils. Now, the compression coefficient, the compression index, can be predicted quite well from the liquid limit. And now we can put all this together and notice that the compression coefficient is related to the liquid limit, the compression index is related to the void ratio at 1 kPa, therefore we can put them all together, and we know from the mathematics of this line that the void ratio at 10 kPa is the void ratio at 1 kPa minus C sub C. Why? Because remember that this is semi-log plot, And the log of 10 over 1 is the log of 10, which is 1. And so we subtract the slope, which is 1 kPa minus the void ratio at 1 kPa minus the C sub C. Now, what about the void ratio at 1 megapascal? Well, this is 1,000 over 1 is 1,000. The log of 1,000 is 3. So it's the void ratio at 1 kPa minus 3 C sub Cs. And this is this value. And with the correlations, then we can predict quite well from the liquid limit measured with deionized water, we can predict quite well what would be the void ratio at 10 kPa and at 1 megapascal. And why did we choose these two values? Because these two values are pretty much the range of stresses that we may find in typical geotechnical applications. This is 1 meter beneath the surface in a saturated system, or meter and a half, and this will be 100 meters. So with shallow formations, but with a foundation on top, this is a reasonable range for engineering applications. If you were going to use this classification for deep formations, for example, for petroleum geomechanics, you can rewrite the equations to work in the stress range of your interest. Very flexible. But let's stick to this for geotechnical near-surface applications. Now, what about the situation with hydraulic conductivity? And so we need a few particles to be inside the matrix of the sand or the gravel to plug the hole. But the problem is that are these particles are going to be stuck on the minerals, or are they going to be floating, and how are they going to affect the hydraulic conductivity? So this is the way we turn around and we say, let's assume that those fines are forming a suspension, and that the suspension is viscous enough to reduce the permeability by 2 orders of magnitude. In other words, the viscosity of the slurry is 100 times greater than the viscosity of water. What would be the void ratio of the fines at that point? And so we ran several tests, and we said, well, at twice the liquid limit, it should flow quite a lot. Well, as a matter of fact, it doesn't. It doesn't flow hardly at all. Very, very, very high viscosity. What about the 3 liquid limits? Well, the 3 liquid limits is flowing quite well. But when we go and try with bentonite at 3 times the liquid limit, the bentonite is very viscous. That means the viscosity of these pastes or slurry does not increase directly with the void ratio at the liquid limit. So let me show you the case for the bentonite. And even at 4 liquid limits, the bentonite has very high viscosity, much greater than 100 times the case of water. Summary, we ran many of these tests, and we recognize that the void ratio for a slurry that has 100 times higher viscosity than water is related to the void ratio at the liquid limit by a factor lambda, and this is the factor lambda. It has to be corrected for the liquid limit itself. The higher the plasticity of the clay, the much higher the void ratio is with respect to the void ratio at the liquid limit. For the study of the liquid, for the measurement of the liquid limit, we recommend methods that really have a significantly lower variability rather than the Casagrande cap. And in all the evidence shows that the British method of the penetrating cone really provides much more reliable and repeatable data. And so we recommend the use of this cone, and this is a 30-degree cone angle here that weighs 80 grams, and we just release it from the moment that it touches the surface, we release it, and we measure the penetration, and we do that for different moisture content, and we see as the moisture content increases, in fact, we do it during drying, as the moisture content decreases, the penetration decreases, and we take the liquid limit as the water content when the penetration was 20 millimeters. Look at here, the data for bentonite is quite inclined. For kaolin, it's steeper. For silica flour, it's quite steep because this is like a sand. it takes very little water from being a solid to being a liquid. That's liquefaction. Basically, a drop of water would do it. And so this is very steep. And notice that diatoms have a high water content because all the water goes into the pores, but it's still very steep because it's actually behaving like a silica flower or like a silt. However, with a high water content because much of the water went into the pores. Now, as we said earlier, we asked for 3 liquid limits when the clay fraction is very important, and this is the case for bentonite. The liquid limit with water is 345 and very plastic. You can change lots of water and the process changes gradually. However, as we do it with brine, now it's not so plastic anymore. We are collapsing the double layers. And if we do it with decane or kerosene, this is behaving almost like a silt. Even a bentonite that when you touch it, it feels like detergent. It's so sleek. By the time we mix it with decane or kerosene, it feels almost like a silt or a sand. And that highlights the sensitivity of the bentonite to changes in pore fluid chemistry. So with those 3 values, now we plot them on these charts, which is the ratio of the liquid limit with deionized water and brine and with kerosene. And we see the different areas, and these are soils from all over the world. And here are the bentonites, and the kaolins are always quite surprisingly weird. These 1-to-1 clays are very different than the 2-to-1 clays. And these are the charts that the system uses to determine both the level of plasticity and the level of chemical sensitivity. In order to fine-tune the boundaries, we compile extensive amounts of data. And here you see the porosity versus the fines fraction, and the porosity is minimum when the particles fill in the voids, and once the fine particles exceed a certain amount, they begin actually opening up. And this is 100% gravel here on the left. This will be 100% sand to the right. And we do that for the compression index, for the friction angle, for the hydraulic conductivity, for both fines and clays with sands and gravels, and sands with gravels. And we even explore many other properties that you will find in the publications that I will cite at the end, including, for example, the suction near the air entry value as a function of clay content for a sand-clay mixture. As you can see in all these trends, these transitions are not happening at 50% for any of the parameters, in particular when clays are involved, and in particular for the hydraulic conductivity. So now that you have seen all these fundamental understandings of soil behavior that lie beneath the revised soil classification, let's go back to the revised soil classification and its operation. Once you introduce the values that we have described before, it uses mass fraction equations that we presented earlier to identify all these transition points with Emax and Emin, and with the void ratio of the fines at 10 kilopascals and at 1 megapascals. Notice that there are blue boundaries and there is a red boundary. We have superimposed the 2 here. So for mechanical purposes, fines control in this upper part and then in this transition part. However, for hydraulic purposes, the threshold for fines control hydraulic conductivity is at a very low level of fines for this particular case. And the system constructs one of these charts for each sediment that you're going to test, and it has internally identified those transition points based on the data, based on Emax and Emin. You may see that sometimes we use values greater than Emax, particularly for the coarse fraction. And the reason is, if you go back to the earlier drawings, the coarse fraction may be touching each other, but really couldn't be in such a loose packing if it wasn't for the sand filling in the voids. However, they are still forming columns sustained and supported by the fines, but those columns are still affecting behavior, until quite a low density of the coarser fraction. This explains these higher transition values, and they are all based on the database. So this is once again the chart. You need to input very few parameters, and it gives you a very insightful classification that will lead to better understanding of the soils you are dealing with for engineering purposes. Just as an example, these are 6 cases here: an angular gravel and sand and a rounded gravel and sand for different, mixed with different clay materials, let's say something like a kaolin, an elite, and a low plasticity bentonite. And as we move to higher plasticity mixtures, the fines, the region controlled by the fines increases dramatically, and the effect on hydraulic conductivity really just a very small percentage here is about 4%. By 4%, you have already filled the voids of any sand or gravel when you use montmorillonite. Now also notice the effect of particle shape of the sand and gravel. As the sand and gravel becomes rounder, it has a huge effect on the region where fines control behavior. So we cannot disregard shape, and shape is intrinsically involved in Emax and Emin. There are several references that will help you go through all this information. And actually, if you go into our website or the Google Scholar listing, you will find not only our papers, but the discussions to our papers, which were most insightful and for which we are most grateful to our colleagues around the world.